Alright, in this video we're going to talk about how to solve, well, just about any force problem that you'll encounter in physics, especially at the high school level or entry-level college level. A force problem is basically any problem that you'll encounter where you have an object of some variety and it's going to have a bunch of forces on it. And we'll go into exactly what kind of forces those forces are and what's going to end up happening to this body as a result of those forces. And we see this every day. When we want to move something, we have to apply a force to it. Whether that's a pull force, a push force, whether we throw something, you're applying some sort of a force to move an object. So let's look at the fundamentals. We're not going to teach you how to memorize 20 different types of problems and simply replicate those. What I want to teach you is how to take any force problem and solve it using more or less the same methods with some variation for the particulars of the problem. So let's look at the most important part of any force problem. That is a free body diagram. Now you saw me sketch a really loose one here. This obviously has no forces labeled or anything of that nature. But a free body diagram is a diagram that illustrates every force acting on a body. And why is it important? Well, it's important because it helps us stay organized and see which forces are acting in which direction. After that, we can use the free body diagram to set up the equation. So it makes it very easy to set up the equations to find whatever it is we're going to find. So a free body diagram should end up looking like some variation of this. With some other possible forces included. We may have a force applied that's actually not horizontal. We could have an applied force that could go this way as well. We could have something else sitting on top of the box, which would add another force. But this is just a really, really general illustration of what a free body diagram will look like. And in that free body diagram, we're going to have forces that always act on a body and some forces that are situational. So let's look at some examples of each. First, we're going to have the absolute truths. And the absolute truths are forces and rules that apply 100% of the time to every body, at least as far as Earth is concerned. And most of our problems are going to be taking place on Earth. And of course, we can adjust the acceleration for other planets as well, but we'll get to that later on. The simplest truth that we need to know is Newton's second law, which is F equals ma. And of course, we're talking about the F net, or the net force. We're not interested in the effect of each individual force on a body. We're more interested in the effect of the two forces together. So let's say we have, for example, a body that is, let's say 20 kilograms. And let's say this body is suspended in the air. So there's going to be a gravitational pull, but we're not that interested in that. There's going to be something supporting that. And let's say we have a little tug of war game going on. We've got two forces here, one going to the right and then one going to the left. And let's say that this person here is going to pull this box with a force of 100 newtons. And then this person here to the left is going to pull this with a force of 120 newtons. Well, obviously, the net force here has to be 20 newtons. If this person's pulling with 20 more newtons than this one, then our net force is going to be 20 newtons to the left. Okay? Now, for clarification on Newton's laws, we can write it in two different ways. We can either write F net equals ma, or we can actually use what's called a summation notation. They mean the same thing. And what that does is that allows us to say that we're not looking for the effect of each individual force, but rather all of the forces combined on this object. So yeah, this force alone, the green 100 Newton, will cause a certain acceleration to the right. This force alone will cause a certain acceleration to the left, but obviously since this force is greater, this object is going to move left. We're not interested in the effects of the individual forces so much as we are interested in the effect of all the forces combined. So both of these equations here mean exactly the same thing, and we can use them interchangeably. Some teachers will prefer F net, some teachers will prefer the summation of F. Either way is perfectly acceptable. And the second absolute truth that we need is gravity. The acceleration due to gravity is 9.81 meters per second squared down. That becomes important a little bit later on when we have to choose axes. We always want to choose the direction of acceleration as the positive axis, just to make our calculations simpler. That will not be the focus of this particular video. And that gravity causes a force downward, and that force downward is called weight. F sub g means the force due to gravity, W means weight. Again, you can use either one. And that force is the mass of the object times the 9.81 meters per second squared acceleration. So you'll actually see that this is the effect of an individual force on the body. So these are two things we need to know, and Fg always acts straight down. Doesn't matter if the body is resting on an incline like this. Fg is always straight down. Even if the body is in free fall and it's not resting on anything, Fg is always straight down. You can think about this in your own terms. No matter how you're standing or laying down or leaning on something, gravity is pulling you straight down. So these two things are absolute truths, and we're going to be using this F net equation quite a bit. So that's one you're definitely going to need to understand and work through proficiently. We can have some other situational forces. Force of gravity acts on every body, everywhere. Problems on Earth, we're going to use 9.81 for the acceleration due to gravity. Other planets and other locations, we may have other accelerations due to gravity. But gravity itself will work everywhere. So what are some of the other forces we could encounter in force problems? Well, here are four that are fairly common. One is going to be a push or a pull force. And we have to be told that something is being pushed or pulled. Generally, we're going to have a rope or something like that pulling this body. And we're going to call that FA. You can just call it F if you'd like, if there are no other forces that aren't labeled. And that's an applied force. It's called an applied force because somebody or something has to apply it, otherwise it doesn't exist. This isn't a force like gravity that is prevalent everywhere. Another force is friction. And friction is a force that's going to oppose the motion. So if we're assuming that we're moving this way, whether it's accelerating or not, let's just say that the velocity is moving to the right, then the frictional force is going to oppose the motion. And again, we're very familiar with this force. Anytime you try to slide something across a floor or move something heavy, let's say you're moving a couch, it's not just going to slide like it were on ice. It's going to be resisted by the friction between the couch and the floor, or the body and the floor, whatever it is that you're moving. Then we have a normal force, and a normal force is the force that acts on any body that is in contact with the surface. So this is a surface force. And it is always perpendicular to the surface. So if you are resting something on a table, the normal force is going to be let's say we're resting something on a table. There we go, we got the pen back. Let's assume that table is horizontal, then we're going to have the FG this way. But if all we had there was the FG, then this book or computer or whatever it is you're resting on the table would just come crashing down through the table. And obviously that doesn't happen, so there must be another force opposing it. Well, the surface exerts a force on whatever object is placed on it, so we're going to call this the normal force. And in cases of the horizontal surface, Fn, the normal force, is generally equal to the force of gravity. We're going to see why that's the case. It's not always the case, because we could have another force acting in that direction. But if these are the only two forces in the vertical direction, the body's not moving in that direction, then the two of them are equal. Don't take that for 100% fact. In some situations it is, in some situations it's not. It should also be noted that if we have something like an inclined surface, then even though the Fg, or the weight, is straight down, the normal force is still going to be perpendicular to the surface. It's basically what's preventing the body from crashing through the surface and just moving on down due to the force of gravity. And even if you have, this is not a problem that all of you will encounter, but if you have a wall and then we have a body resting on that wall, well, it wouldn't be resting on the wall per se, but it would be pressed up against the wall. Fg is going to be this way, and Fn is actually going to be this way. And you can try this by just taking your hand and pressing it on different surfaces. If you press it on the table, you're going to feel a force from the table pushing up against your hand straight up. If you press it on a diagonal surface, you're going to feel that force acting diagonally. And if you lean on a wall and you keep your hand parallel to your arm parallel to the floor, then you're going to feel that force coming back at you from that wall, keeping you from crashing through the wall. And finally, we have tension. Tension is useful if we have ropes connecting different things. Tension is basically the force due to a rope. Or a string. And is specific to problems that use ropes and strings, like pulley problems, Atwood machines, and things of that nature. So, let's see how all of these things act together. Let's look at an example. We're going to put this all together on one simple free body diagram. We have a 16 kilogram box, and it is being pulled. So we've got our applied force here that is pulled along a horizontal surface. Now this is important information that tells us that the surface is straight horizontal and that there are no angles between the horizontal and the surface. And that also tells us that the force of gravity is going to be on the y-axis. We're going to see why in a second. And that force is 80 newtons. And we're also told that that force is parallel to the surface. So again, this problem is pretty simple. We're not going to be angling the force. We don't have to break anything into components. This is relatively straightforward. Now we have some other information here. We have the coefficient of kinetic friction, which is mu sub k. And we're going to get to that as well. There's a formula for that in the physics reference table. And after you've done a few friction problems, you should be very familiar with this. And then we're looking for the acceleration of the box. So our A is our question mark. So let's draw a simple free body diagram. I'm going to draw the surface. We'll assume that that's horizontal. And I'm going to put a 16 kilogram box resting on this surface. Okay, that's the mass of the box, and it's simply sitting on this surface. It is being pulled along along the horizontal surface by an 80 Newton applied force. So right away I'm going to say FA is 80 newtons. Now, what other forces are acting on this body? Well, we've got the force of gravity, or the weight, and that's going to act downward. And we know that that is always m times g. We're assuming that this is on Earth since we're not told otherwise. Then we're going to have a normal force, which is going to prevent this box from simply crashing through the table. The table is going to support the box. And we don't know what that is just yet. And we are told that there's a frictional force. So I'm going to put a frictional force here, because we're going to assume that we are moving to the right, since that's where the applied force is going. If you were to draw this free body diagram backwards, that would be perfectly fine. You just have to make sure that the left is your positive axis. So, a couple other things that we could do here. We could definitely calculate the FG right now. We could just put the 16 and the 9.81 right away. That would give us our FG. But that's not completely necessary at the moment. What we want to do is take all of this and set up two simple equations. One in the x direction. We're going to have an x-axis going this way. And one in the y direction. Going this way. Those are the two axes that we're interested in, and every force right now lies on the axes. So this should be a really, really, really easy problem to solve, since we don't have to put anything into components or anything of that nature. So we're going to go ahead and we're actually going to copy this entire piece here. I'm going to go ahead and move this entire piece over here. So let me just position this so we can see everything. Nope, not that. Here we go. Now we have all the information we need. And now we can set up our two equations. And remember the fundamental equations from over here, from Newton's laws. We're going to start with this F net equation, or the summation of F. Now I'm going to use summation. You could use either one. It doesn't make any difference. So I'm going to say, okay, the summation of all the forces along the x-axis, in this case there are two, is going to give us MAX, because that is a Newton's law. We know that to be fact. And I'm also going to set up a second equation, which would be the summation of the forces in the y direction is going to be MAY. The next step is to ask yourself the following question. Are the forces accelerating in the y direction? Clearly, since we're moving it across the horizontal surface, as described in the problem, the acceleration in the y direction is 0. And that's going to be the case more often than not when we have a surface type problem. So we can say safely that the net force in the y direction is 0. Because acceleration in the y direction is 0, so it does not matter what the mass is, the right side will be 0, as anything multiplied by 0 is 0. Well, now let's consider that we're going to have a positive y-axis up and a negative y-axis down. And we can say that the forces in the y direction, the net force in the y direction, is equal to Fn minus Fg. Again, because this is going down and this is going up, so they are in different directions, and we will take up to be positive because that's conventional. And that equals 0 because we know that the net force in the y direction has to equal 0. So now we can say, okay, Fn must equal Fg, and we can actually calculate what Fg is. We talked about this on the previous slide, and it is 16 times 9.81, which is 156.96 newtons. So, now that we have that, we can look to set up our x equation, and here we do have an acceleration in the x direction. We know that, because we're being asked for it. The problem is asking, what is the acceleration of the box? So clearly there must be an acceleration to the box. And of course, since we're moving horizontally, we can assume that the acceleration is horizontal. So, well, what is the positive force acting in the x direction? That's going to be Fa. Fa is going to be the force that makes the motion happen, whereas Ff is going to oppose said motion. So Fa minus Ff is equal to m times a in the x direction, which is what we're trying to solve for. So let's fill in what we know. We know that the applied force is 80 newtons. We don't know Ff just yet, but we can calculate that. We also know that the mass of the object being moved is 16 kilograms, and the A is what we're trying to find. So as it stands, we can't solve this because we have another unknown here in the force of friction. However, we know the normal force. And since we know the normal force, we can go to our physics reference table if you have not yet familiarized yourself with this equation and find the equation. The force of friction is equivalent to mu, which we were also given, times the normal force. So since the force of friction is mu times the normal force, we can calculate the force of friction. The mu is given to us in the problem. It is 0.15. And the normal force from here is 156.96 newtons. So again, we're going to take it to the calculator here and say that our Fn times the mu, so 0.15 times 156.96 is equal to 23, I'm going to put that up here, .54 newtons. So now I'm going to take that and I'm going to substitute that in for the FF here, since now we know the value of FF. And I'm just going to get rid of the units for the time being to simplify the algebra. And we've got 16 times A here. So all we have to do now is do the subtraction on the left side, which is going to be 56.46. And that's going to equal 16A. And we're going to divide both sides by 16. And 56.46 divided by 16 is 3.529. And that is in meters per second squared. We'll skip using the units in the intermediate steps, but you absolutely, positively must have your units in the final answer, especially if you're being asked for an acceleration, a force, or anything of that nature. If you're asked for the coefficient of kinetic friction, there are no units there. So, and that's basically the gist of it. You can take this system and the information given to you in the problem, which will vary, and use it to solve every force equation ever as far as high school and low-level college physics are concerned. All you have to do is figure out the different types of forces that we're going to be introducing throughout the year, some of which are going to be electrical forces, magnetic forces. Centripetal force is going to introduce another axis as opposed to just X and Y. And we'll also have to add the concept of components and breaking down a force that isn't on an axis. So let's say that the person pulling this object wasn't pulling it horizontally, but rather pulling it at an angle like this. So we'll talk about that in our next clip, which is going to expand on this, but use exactly the same tactics, just simply use a few more forces and make it a little bit more difficult. Thank you for watching.